Thanks to everybody for who's watching today. We appreciate you being here. My name is Dr. Stephanie Morley, and I'm the president of Vetlen. Vetlen is proud to bring you a new awesome device called the Vetlen Pouch. It's a local drug delivery device that allows for antibiotic diffusion directly where it's needed most. We have talked to so many veterinarians over the last year or so and gotten tremendous feedback, but there are a few questions we have consistently gotten. One of those is, how do I use the pouch? And one of them is, how do I know I'm going to get effective antibiotic doses in the wound? How do I know I'm going to get the levels I need? So we thought, who better to bring on and talk to you about those questions and more, but Nic Ashton, who is the co-inventor of the product and a member of our team. So thank you for joining us, Nic.
Excited to be here. Thank you.
Absolutely. So I have a whole bunch of questions for you. First of all, the one everyone asks, tell us a little bit about you and your background.
So I grew up about 50 miles south of Salt Lake City in a college town called Provo, Utah. My grandpa was a plastic surgeon, reconstructive surgeon, so I did hands and face. So I kind of grew up in the shadow of him showing. He was also big time into stereo photography. So I'd get these, stereo viewers and see people's faces laid open. And at some point you just kind of, it just becomes part of the background noise, right? But yeah, he was a pretty awesome surgeon, one of the few reconstructive surgeons at the time down there. And I grew up playing in my other grandpa's orchard as a young child, and I have a really awesome uncle who he was an engineer going through a pretty bad divorce at the time, but lived in my grandparents' basement for a while, and he kind of took me under his wing and showed me how to use the shop. So it's kind of two parts pulling me, engineering side and medicine. So I decided to split the difference and came into medical devices. So I got 3 degrees in biomedical engineering at the University of Utah, and came to work for Dustin because he had an awesome idea. Dustin's the other interviewer, but my senior level mentor as a postdoc to work on this exact technology we're talking about today.
That's great. I love what brings people into what they do for a living. So first question everyone truly asks is, how does the Vetlen Pouch work?
Okay, so I read these questions ahead of time, and I'm going to be a little bit persnickety here.
Okay.
There's how the pouch works, the physics behind the device itself, and then there's the question of why it works, which is I would kind of put it more in the camp of the biophysiology that's occurring for the pouch to function. The pouch, and this is where I told you I was going to share one screen, and I can't, as an engineer, in good faith, get through a presentation without sharing an equation, right?
Okay.
So knowing that the audience is a bunch of very intelligent medical experts who've been through various physiology courses and at least have touched on this at some point. So I'm going to bring it kind of back into their memory. You see this equation here?
I do.
So this comes from Fick's first law of diffusion, or this is Fick's first law. So when you hear the term Fickian diffusion, this is effectively what gets it going. And that first term there is flux. So think about the total amount of drug or material moving across a certain surface area, right? So in the case of the Vetlen pouch, we've got a rate controlling membrane. Okay, so that's the surface area. You would kind of think in that context. But the pouch operates on principles of diffusion. And the second term here, the minus D, that is your diffusion coefficient, so how fast the drug randomly moves through water. That's a Brownian motion of the drug effectively. And then that d phi over dx, that's the concentration gradient, where phi is the concentration and dx is the distance. So it's the concentration across any given space. So if you're thinking of the pouch, think of the concentration on the inside of the pouch, concentration on the outside of the pouch, the rate of diffusion, the diffusion coefficient inside the pouch's membrane, which is the rate controlling component of it. And you see the large driving force. And that's why I bring up this dumb equation, is that d phi dx is the driving force for the pouch to operate. So very large diffusion gradients, meaning high concentration in the pouch, there's no drug in the space around it, will lead to faster release of the drug. So that's its physical operation. That's how the device works. And you add to that a daily refilling, and you can maintain high internal concentrations of drug, which means you're maintaining a high driving force, and the device is continually releasing. The driving force diminishes over 24 hours, and then you top it back off. But that equation is really, really key to how the device works. If you let me, I'm going to jump into the why the device works, which is kind of the physiology of the device. And I think it's probably the more telling component, probably the least understood by medical professionals. And really what's going on is that I say you, animals, humans, we're all relying on a vascular network to deliver nutrients and oxygen to our tissues. In fact, there's no cells in the body that are more than 50 to 100 microns from the nearest capillary. In fact, many times you get capillaries on all sides of that one cell, wherever it be. And that 100 microns is a pretty critical distance. And the reason is diffusion time is proportional to the square of distance. So as you get really, really large spans, really large distances, your diffusion capabilities alone don't work to deliver nutrients, which is why our bodies, animals' bodies, use a facilitated diffusion system where you pump the blood to within 100 microns, the rest is diffusion. And then that is how it works in the body. After 150 microns, the rest is diffusion. That's about the distance that you can deliver things via diffusion. And so what we see happening in infection is you see a breakdown of local vasculature. And there's a bit of a misnomer in many of the microbiological textbooks, but effectively all of the organisms that cause these opportunistic infections, the ones that are just out in the world, you swab any handrail, you'll find these opportunistic pathogens. They are all facultative anaerobes. They can both undergo anaerobic or aerobic metabolism, and they're perfectly happy doing anaerobic metabolism in confined spaces where they've devascularized the space. And that's actually why, that's kind of the underlying principle of why you see an infection in a clinical scenario where you've got a positive culture, you're using an antibiotic that should work, and the infection still keeps raging. It's because you've got large tracts of tissue that are beyond the diffusion capabilities of the vasculature. And so that gets into why the Pergo pouch works, is that when you've had breakdown in local vasculature and you're not getting the drug there, if you put the pouch exactly where you want it, and you dose it with very high amounts of drug, you've got a field of antibiotics where you normally couldn't get them systemically. And you can maintain it by refilling the device. Yep.
Okay, a great addition to the question. Thank you. And I should say as a side note, Pergo Pouch and Vetlen Pouch are the same product.
Oh yeah, do I keep saying Pergo?
No, you've said it once, and I just want to clarify.
It's the same technology.
It's the same product. Yep. The Pergo Pouch is being developed right now for human medicine. It's on its way through that process, but we brought Vetlen Pouch to veterinary medicine first. So, okay, so another question that's asked repeatedly, because we talk about what drugs we have diffusion data for to say this can effectively be used in the pouch. The main characteristics of those drugs is water solubility. So why does a drug need to be water soluble to dose the pouch?
Yeah, so this is actually another reason I wanted to present this equation today, is because the concentration gradient, the amount of drug on the inside and the outside, is not calculated off how much drug you can fit inside the pouch. It's calculated off of the soluble phase of drug that's inside the pouch. So if you have precipitated crystal inside of their pouch that doesn't go soluble, you're only counting the stuff that's actually in solution as it relates to that concentration gradient, if that makes sense. If you want a high driving force, which leads to a high diffusive field around the device, you want to use a drug that's water soluble. And importantly too, there are a lot of antibiotics that have been identified in nature that were never translated into clinical products. A lot of times these are insoluble compounds, and a lot of times the steps that your physical chemists, your pharmacists will go to convert one of these natural products into a usable antibiotic is actually solubilizing the drug, putting some functional group on it that makes it go into solution. Us being big bags of water, it turns out that most antibiotics are pretty soluble. And that's by design. If you want good distribution in the tissues, you need stuff that goes into a water phase. If that makes sense.
It does make sense. So why is it best? We recommend when dosing the pouch to dose at the highest daily dose that you're able to place inside of the pouch. Why do we recommend that the highest antibiotic dose be used despite the fact that we're getting local delivery?
Yeah, that's great. That's a great question. So if you think about we talked about the components of the vasculature as it relates to capillaries around the surgical site. There's also another field of diffusivity, or another component of that field. And when the fluid flows through the capillary, a little bit of it oozes across the fenestrations in the front end of the capillary, and that leads to the origin of your lymphatic system. And the lymphatics are bathing everything, and they're very slowly changing out the concentration. So they call it a lymphatic perfusion rate. It's usually calculated as a percent per hour. And in lymphatics, you can vary anywhere from around 3% in healthy tissues, percent per hour turnover, all the way up to 15% to 20% per hour in exercising muscle. If you think about the dynamics in our surgical site or in an infected site, you can go all the way down to very, very low turnovers before the tissues then start to die when you get into the single digit, 1% range. And so our greatest liability for infection happen to be those very poorly perfused tissues. But we also have the perfused tissues around the pouch that are removing antibiotics actively from the site. So what you're trying to do is create the largest diffusive field around the pouch. As you create that, at distances away from the pouch, the lymphatics are slowly effectively fighting against the concentration of the antibiotics in that space. So you want to go as high as possible, so that you are going to deliver antibiotics systemically. The dynamics are different, but they do go systemic eventually. But you really want to create that very large diffusive field, which is being fought against through the local lymphatics. That makes sense.
Okay. Yeah, it does make sense. So that kind of leads into the next question, which is, how can veterinarians be assured that the level of antibiotic that they're going to see locally is truly at efficacious levels?
Yeah, so the efficacious concentration of antibiotics we usually use this term clinically, and everybody's, all the veterinarians will be aware of it. We use a MIC value, which is the minimum concentration that will inhibit division of the microbe. With some caveats. It's the minimum inhibitory concentration with it's a 10 to the 5 inocula level of bacteria, which is kind of a clinical. It's a quantitative microbiological threshold for defining infection. So I use 10 to the 5 inocula. Your MIC value actually moves around if you use more or less bacteria. The MIC value also moves around based on the media, if there's tissue present and things like that. So you'll see efficacious ranges being, maybe an order of magnitude 10x the MIC value, like take amikacin or tobramycin, any of these aminoglycosides. You typically have an MIC value of around 1 micrograms per mil. You're going to see serum levels that'll probably be, 5 micrograms per mil, or 10, 20 maybe max. So you want to be above that, because then you've got a field that's inhibiting division of the microbe. And so your original question was, and I apologize, keep me on course here, Stephanie.
No, you're fine. Just that, how can veterinarians be assured that the doses they're getting, the levels they're getting in the wound, dosing locally, are truly efficacious?
Yeah. So we've built, and you'll see this in the white paper for anybody who wants to go dig, we've built some diffusion models for simulating how the device releases. And in our most, we can do boundary testing in that. What happens if the tissues aren't perfused? What happens if they're perfused at an insanely high rate? What happens if we load it with X amount of drug? And what we find is that in all cases, these extreme boundary conditions, there's always going to be some super MIC concentration, even at the end of 24 hours immediately adjacent to the pouch. So you always have some efficacious field around the pouch with the vast majority of antibiotic protocols you will load. The pouch really does create very high super MIC levels immediately around the pouch. As for how you can know, I think that's a clinical outcome, right? Infection is defined by clinical metrics. So you're going to look for the signs of diminishing infection. And at least in our animal models, you tend to see the signs fairly quickly. Diminished inflammation, diminished wound drainage. Wound drainage is usually promoted by infection. It'll cause lots of stuff to migrate to the field. So the clinical outward signs of infection. But I think with the vast majority of protocols we've recommended for dosing and dosing guidelines, even at the end of 24 hours, you'll still be above, somewhere around the pouch, above the MIC value.
Okay. So we have a couple of products that veterinarians have used for years for local drug delivery. And one of them that's a primary candidate for that use case are calcium sulfate beads, antibiotic
Yeah.
impregnated. So how does the pouch compare to beads?
Yeah, that's a great question. So the Pergo pouch, as I described, is like if you want to go digging in the literature, everyone wants to read about this. It's what fits into it's what's called a reservoir core system, or a core shell system is another name for it. And that's where you've got this rate controlling membrane, you've got a drug on the inside. These other approaches, be it calcium repurposed bones, I guess in humans it's repurposed, but for animals, the labeling's a little different. But if you're loading effectively plaster of Paris full of drug, that is what they call a matrix system. And the diffusion dynamics are a little bit different. But the key here is that our device isn't just a core shell system, it's a refillable core shell system. So with the other products, they do deliver super MIC concentrations for some time. And I'm not in the business of bad mouthing other products. They have a place. I tend to view it, I went into medicine to try to help people and to try to push the envelope. They have a place. And I like to give the surgeons every possible tool they can to manage. Like having done the surgeries myself in animals and sat and watched our clinicians work, these are really messy environments. They need every tool they can have. But in the case of the Vetlen pouch, if you consider, just take amikacin for example, or gentamicin. In a large animal, you're pushing a gram of that drug a day, and you can refill the pouch every day. That's several grams, many grams, 10, 20 grams over the total course of treatment through the pouch. You can't physically create a product that holds that much material on it in a coating form or a gel form. And so these products that aren't replenishable, they come at a cost. And the cost is you lose payload very quickly because of the lymphatic perfusion that we talked about. And once you drop below the MIC value, any residual matrix that is left behind can become a nidus of infection. In fact, in one of our animal studies, we actually had to pivot course. We wanted to use a calcium sulfate product as an antibiotic carrier to test an antibiofilm compound we were doing work on. And we wanted to use it as an aid to test this hypothesis. And what we found in our early parts of that study was the calcium sulfate potentiated infection once it dropped its payload. And it made everything worse, even worse than our positive controls of infection. So that's not to say the product doesn't work. It just means that in very high infection rates, or sorry, I shouldn't say rates, very high infectious loads, so very aggressive infections, these products could become, at least based on our animal work, could become a liability after they drop their payload, because you're leaving foreign material behind that is well below its MIC value. In fact, the highest concentration of microbes I've ever seen in any of our animal models was actually explanted calcium sulfate beads once the bacteria migrated up in. So the pouch works because it sustains its payload. And, kind of related to that, the matrix that's controlling the delivery here, or the shell system, is removable as soon as you stop dosage. So you can remove the device like a surgical drain. Yes.
Yeah, wonderful. And I just realized we still have your formula up. So if you don't need that anymore, we can take it down.
Well, I want everybody to know it. No,
okay. There's a quiz at the end, right?
Yeah.
All right. Okay, so we talked about why the antibiotic needs to be water soluble when dosing it in the pouch. And in our dosing recommendations, we talk about a loading limit. This is essentially what's the limit of concentration of drug that can be placed inside of the pouch. But what if the dose exceeds that solubility or that loading limit? What's going to happen inside of the pouch?
Yeah, so there are a couple of things here. One thing that I think everybody should be aware of is just because an ampule of drug that's provided looks soluble, meaning it's transparent when you put in your solution and reconstitute it, doesn't necessarily mean the thing will stay soluble once it goes into the pouch. That's why we kind of urge caution to go off our tables as opposed to going off of, oh, it looks like it's fine. So what will happen is, usually in a lot of these compounds that appear to be soluble but aren't, or have low solubility, they have ions or other surfactants or emulsifiers that keep them in solution. And those will also move across the membrane. Ions move quite a bit faster across the membrane, and it can cause that solution to then crash out. And you end up with a precipitate inside the pouch. If you're kind of straddling the range of solubility, you can, as that soluble phase leaves, the crystals will then solubilize and you'll deliver more drug. So it's not, there are some drugs that are borderline soluble that actually can be delivered through the pouch. You just won't be delivering as high of percentages. You'll actually have a more steady state release in those scenarios. One drug that we've worked with is metronidazole experimentally, and it has a solubility around 5 mg per ml. We're loading it at 20. We never got soluble drug out of it, so it was going into solution over time, but it would have been a much more steady release. So one approach, if you want to deliver a drug through the pouch and you're kind of optimistically or cautiously approaching this, you could give the dose you want to give, but just pay close attention on the second day when you draw the drug out to see if you're getting precipitate. And that precipitate can build up over time if it is there and actually lead to the pouch, difficulty getting the pouch out because you now got a bolus of material that's not going to collapse. But you can dose other things through it that are kind of borderline soluble or insoluble. It's just you've got to approach it very cautiously. I don't know if that's what you wanted me to tell people, Stephanie, but
Yeah, I think, one of my next question was to talk about how we have tested like lidocaine and other insoluble drugs, because we routinely get the question of whether we can dose with lidocaine. So I guess, talking about the mechanics of it and everything that you've explains why you shouldn't use a water insoluble drug. But if you did use an insoluble drug, then we're basically suggesting to people that they should be looking for signs of precipitate. And at that point, if that was the only drug you could use, then they could be flushing that pouch with saline until it becomes clear and then redose, correct?
That's right. Yeah. So if you wanted to keep using an insoluble drug and think you're getting efficacy, and you very well may be, because it will be delivering, and it'll be delivering in a pretty steady state release. You'll just want to make sure that you're able to get that precipitate out every day it exchanges so that it doesn't build up. And you would do, and there's a bit of a safety component to that as well. If you have precipitate building up day after day after day, then you have potentially above above a maximal dose that's actually in the pouch sitting there. And if the pouch fails, maybe it fails because you're trying to pull it out and the thing hasn't it hasn't collapsed all the way because there's precipitate. You risk potentially exposing the system to a more than a maximal dose. So there's a bit of a safety, but if you can go in and flush it with saline, get it out, and then restart it every day, yeah, it's perfectly fine.
Okay. We had Mark Papich did an analysis for us where we compared the serum concentrations of amikacin from animals who were dosed via the pouch versus dosed systemically. And if you could just talk a little bit about why that comparison was important and what that can mean for the safety of dosing via the pouch.
Yeah, that's a great question. So amikacin, as well as a lot of other antibiotics, because they're highly water soluble, they're taken up very quickly if you give them intramuscular or IV, right? And they're taken up quickly IV. That's kind of the point of the IV. So you get this really rapid spike in initial dose 20, 60 minutes after for the aminoglycosides. I was actually just looking at the publications for tobramycin on this the other day. So rapidly peak. And I think in his paper, if I remember right, he was using a PKSim software. It's pretty standard software in the field to simulate, here's what the dose would look like in this animal. And that's got good white papers. It's very well tested, well recognized. Is that here's what the pouch is doing, and it's getting nowhere near these maximal peaks. Part of that's because the pouch releases its drug into those sites very, very slowly. And so if you're looking at the area under the curve, it might be more comparable, but if you're looking at the maximal doses, it's nowhere near the pouch. So the pouch doesn't exceed those safe thresholds, or at least it's a safer way to go from a systemic perspective. And I know the Papich paper, they're particularly interested in amikacin because this has the ototoxic or neurotoxic effects. So if you can take these drugs, I've been a long advocate for as it relates to the pouch. And if you can use an aminoglycoside and you have an effective aminoglycoside, I would dose that through the pouch. And then I would probably layer that with a systemic beta-lactam therapy. That would be the kind of the go-to. And the reason for that is because of kind of what Papich showed in that paper was you can have much greater diminished, or you can actually cut your dosing and still have super-MIC levels around the pouch. So you can minimize those effects of those aminoglycosides, which no one really wants to use them. kind of get forced into having to use them. And then you get layered efficacy with the beta-lactams. And also, I should add, the aminoglycosides are well known to be synergistic with beta-lactams. That's been like established since the 70s.
Great. Okay, here's another question that I didn't prepare you with. So one of the questions I get pretty frequently from people who are using the pouch is on the residual fluid volumes that they get and how they can vary. Sometimes they'll get, if they're dosing in a 10 ml pouch, they might get 2 mLs one day and 8 mLs back the next day. Some people get consistently 9 mLs every time they go to do a drug refresh. So I know there's a lot of variables that can impact that residual fluid, but can you speak to what those variables are and why veterinarians should feel confident that they've actually released drug and that they're not pulling effective drug out?
You mean with variability in amount of volume they retain?
Yes. Yeah.
So the pouch, and maybe this is when I talked about the physical principles early on, it was a bit reductive. We talked about the diffusion characteristics. There's also another delivery mode in the pouch that operates. And that delivery mode, it's kind of unintentional. It's an unintentional byproduct. That happens to be a pressure gradients across the membrane. The membrane is a resistive element in its own right. So if you think back to your physics, the Ohm's law equations, those effectively apply to fluid dynamics. So if you've got your pressure gradient across the membrane and a defined resistive component to it, you will have fluid flow, and it's a linear relationship. So what that means is that the pouch, in some situations, because of external pressures in the musculature, the animal sitting on it, the materials in the pouch relaxing back to zero, the pouch will lose some volume over time. And that's actually accounted for in our models that we use for modeling the pouch in the white paper. I believe it discusses that. If not, it is in the model and it just didn't make it into the white paper. So that's another way that fluid can get into the site from the pouch. It has a pretty negligible effect on the total percent released at the end of 24 hours. It can change the shape of the curve over 24 hours, but it doesn't. We're small percentage differences at the end of 24 hours. So people should rest assured. And one of the things that can happen, like if you're one of those veterinary surgeons who's doing horse work, your max daily dose is insanely high compared to smaller animals. And that means they're loading the pouch with very, very high osmotic concentrations of drug, which actually means that pouch will pressurize. It will pull in fluids externally right out the gate. And then once it hits that osmotic equilibrium, because the pouch can withstand quite a bit of pressure, it'll just sit there and hold its volume until drug diffuses out to then reach parity with the osmotic gradient with the tissue, and then it starts collapsing slowly. So you can actually see in larger animals with very high doses of drug, you actually see the pouch stay inflated a lot longer and then start to decrease. So for any surgeons using this, particularly the equine surgeons, they might be recovering 100% of the drug or the volume every day, and that's probably because they've got osmotic gradients that are very large throughout the duration of the course of treatment. It doesn't mean the drug's not diffusing. It just means that they've had such high concentrations that it took forever to equilibrate.
Okay, awesome. Okay, so this product better than anybody. Is there anything that we haven't touched on that you feel the veterinary audience should hear about?
A good question. I mean, I kind of spilled my guts on the technology behind it. I would just add that we've in our lab, Dustin, the other interviewer, my senior mentor, this device initially, and this is one of the things that really impressed me with Dustin as a postdoctoral fellow. I came on board to help build this device. He had a concept. I hope he was honest with how he presented that concept. He had a beautiful concept. It's all his idea, but we had to make it into a buildable product. And then, to his credit, and this is what I loved about Dustin, he had really good, very aggressive biofilm related infection models. So we're talking the kinds of infection models that don't respond to antibiotics, even though you're using an antibiotic that is an organism and an antibiotic that's susceptible, right? So he was building these infection models that mirror what we see in clinic. And that appealed to me. One of the reasons I came on board in his lab was because I just wanted to be familiar with infection models as a postdoc. Like I said, that's a valuable life skill. And to his credit, what he wanted to do was take the pouch and do what I refer to as the kill test, which is this going to work? Because in 100% candidness, the device is insanely stupid. Like, it's a very simple device, and I say that endearingly. And as a biomedical engineer who's been doing this kind of stuff for years, as a student and a graduate student, I say, why has this not been done yet? Right? That's the obvious question, because it's pretty obvious. We just reload something and put it in the field. We effectively have a matrix. We just reload it with drug, and we'll work better. And Dustin's models, one of the reasons why it hadn't been done yet is because there's misconceptions about the nature of infection as it relates to capillary beds, but also because there's just a lack of labs that do good models for training their devices. So if I could relay anything to anybody watching this, is that we trained the device and we intentionally built it against very aggressive infection models, which I believe mirror very well the worst kind of cases you see in the clinic. And so if you're a veterinary surgeon on the fence saying, do I want to use this or not, this is the absolute best device to use for the most aggressive infections that aren't responding to your antibiotics, even though you have a positive culture. This is the case. This is how you want to use it. That's how the device was developed. And we weren't looking for a way to sell a product because we just didn't know what to do with something we built in the lab. We legitimately built this and trained it against infection models for this exact purpose. So that's the part that I'd like to relay to anybody watching this, is that it was designed, and we would have wholeheartedly thrown this device out and gone with any number of other technologies we've been working on to not pursue a dead end. Like, to Dustin's credit, he was willing to pony up. He had some activity funds. It wasn't tied to a grant. He was willing to pony up those activity funds to do a kill test and four sheep initially. And we were actually blown away with how well it worked. So the stupid device that should have been on the market 10 years ago worked exceptionally well for the reasons we talked about. And to Dustin's credit, it was because he was willing to do a kill test and scrap the project if it really wasn't of clinical value.
Great. I appreciate that. Well, thank you for taking the time to chat with us. Thank you for all your work for the Vetlen Pouch. And I promise we'll bring you every other question we receive out in the field, and maybe we'll be back to have another conversation.
Yeah, for sure. Love it.
All right.
Thanks,
Nick.